Hello everyone, welcome to the Mechanical Studies. In this video, we will study work and heat transfer. Thermodynamics basically deals with conversion of energies in the form of heat and work, and therefore it is essential to study these forms of energy. Remember at first here, both these work and heat are energy interactions. That means these are energies in transit or energies in transfer. In a simple way, we can define work as transfer of mechanical energy and heat as transfer of thermal energy between system and surrounding. Thus note here an important point that a system does not possess heat or work. Actually, system undergoes a change as a result of work and heat transfer. Okay. There are several forms of work that you will come across, like shaft work, spring work, electrical work, and so on. The important one that we must include here is displacement work, or also called as moving boundary work. This work is associated with expansion and compression of gas or vapor in a piston cylinder device. For example, internal combustion engines or reciprocating compressors. Okay. Let's consider here fixed mass of gas enclosed in cylinder and piston having cross-sectional area A. Now here the gas exerts pressure P on the piston so that it will cause to move upward with force F. Okay. Now if ds is the small displacement of the piston in upward direction, then the differential work during this process will be given by del W will be equal to force F into displacement ds. Now here force F can be written as pressure into area, as pressure is force upon area. So this force will be equal to pressure into area and remaining term displacement. Now here area into displacement, A into ds, area into displacement, it will be change in volume dV. So we can write differential work del W will be equal to pressure P into change in volume dV. Okay. Now if this system undergoes a process in quasi-static manner from initial condition 1 to final condition 2, then the total work during this entire process in between state 1 and 2 can be written as W12. This will be equal to integral of del W in between limits 1 and 2. So this will be again written as integral of del W is here P into dV, P into dV, and in the limits integral over the limits 1 to 2. Here the unit of work will be joule or kilojoule. As you can see here, the work here is the function of pressure and change in volume dV. That's why this displacement work is also called as PdV work. PdV work. Now please note here very important point that you can use this formula W is equal to integral of P into dV in case of a closed system undergoing a process in quasi-static manner. But don't use this formula for open system devices, since those are analyzed on the basis of steady flow energy equation, which we will see in later videos. One more important point here regarding the work is that work is a path function, which is dependent on the path followed by a process. For example, here a system undergoes 3 different processes in between same initial and final condition, that is 1 and 2. Here work interactions involved in three different processes will be different, as you can see, since the path followed by these three processes are different, and that is why work is called as a path function, because it depends on the path followed by the process. Now work is inexact differential, and that is indicated by del W, not dW. Okay, that means if we take integral of del W in between the limits 1 and 2, this will be represented as W12, and this is not equal to W2 minus W1. This is what the meaning of inexact differential. On the other hand, exact differential like volume represented by dV, not del W, and if you take integral of volume dV over the limits 1 to 2, this will be equal to now V2 minus V1. Okay, this is what the difference between exact and inexact differentials. Okay, so here you may find that the exact differentials like volume, temperature, entropy, internal energy serves system properties. Now let's go to another form of energy, that is heat. Heat can be defined as the form of energy that is transferred between two systems or between system and its surrounding by the virtue of temperature difference. Okay, that means the very first requirement for the heat to be transferred is what? Temperature difference delta T. Okay, whenever there is a temperature difference, heat will transfer from high temperature to low temperature either by conduction, convection or radiation. So please note here, a process in which there is no heat transfer between system and surrounding is called adiabatic process. Adiabatic process. Okay, one can achieve adiabatic process by maintaining system and surrounding both at same temperature, so there will be no heat transfer, or by providing strong insulation over the system boundaries. Just like work, heat is also a path function which depend on path followed by a process, and it is also inexact differential. Now let's see some more aspects of work and heat here. In case of work, we have seen right now that work is function of two properties. One is intensive property, that is pressure, and another is extensive property, volume. Therefore, in thermodynamics, pressure volume plots are used to describe a process that involves work interaction. Okay. Now note here, area under a curve or process on pressure volume diagram gives magnitude of work associated with that process. On the other hand, in case of heat, heat is also a function of two properties. One is intensive property, which is temperature here, and second is the extensive property, which is called entropy. And that's why in thermodynamics, temperature entropy plots are used to describe a process that involves heat interaction. And note here, area under the curve on temperature entropy plot gives magnitude of heat associated with that process. If we look at the sign conventions of work, work done by the system, that is work of expansion, will be considered as positive, whereas work done on the system, that will be work of compression, will be considered as negative. Whereas in case of heat transfer into system, that will be called heat supplied, will be considered positive, and heat transfer out of the system, that will be called heat rejected will be considered as negative here. Okay. Now let's look at the similarities between heat and work here. Both heat and work are energy interactions. Those are transport phenomena. Second, both are boundary phenomena. That means you will observe these at the boundaries of the system and surrounding. Then both are associated with process, not a state. And that's why heat and work have no value at state. And last, these are path functions and inexact differentials. That's why these are not system properties. Okay. Now at the end, let me tell you about different terminologies and notations you will find in these subjects regarding this heat and work, so that it will not create confusion. Total amount of work or heat transfer, that will be denoted by capital letters like W or Q, and their unit will be joule or kilojoule. Okay. Whereas the amount of work or heat transfer over the period of time will be expressed as a rate of heat or rate of work transfer, and that will be denoted by a capital letter having dot over the head like W dot or Q dot, and their unit will be kilojoule per second. That means kilowatt. Kilojoule per second is kilowatt. Sometimes we are interested in the amount of work or heat transferred per unit mass of the working substance, and that will be denoted by small letters here like small w and small q, whose unit will be kilojoule per kg. Kilojoule per kg. Okay. Thus here for heat I can write total heat transferred will be equal to mass of the substance into specific heat transfer, small q, or rate of heat transferred will be q dot. This will be equal to mass flow rate m dot into specific heat transferred, small q, where small m is mass, that will be expressed in kg, and small m dot, that is mass flow rate expressed in kg per second. Okay. In this way, I have covered various aspects of work and heat transfer, their sign conventions and significance of pressure, volume and temperature entropy plots in this video. Thank you.